Tonight, we're going to explore one of the most unsettling truths about the worlds that share our cosmic neighborhood. Every planet around our sun, from the molten cloud decks of Venus to the radiation-soaked plains of Mercury, is engineered, by physics alone, to kill an unprotected human in minutes. On Venus, the atmospheric pressure is 92 times Earth's, the equivalent of standing 900 meters underwater, deeper than any human diver has ever gone. The surface temperature is 475 degrees Celsius, hot enough to melt lead, hot enough to melt zinc. A spacesuit rated to 500 degrees would buy you about 20 minutes. The Soviet Venera 13 lander, the toughest machine ever sent there, survived 127. And yet Venus may not be the worst place you can find yourself. Some worlds kill instantly. Some kill slowly. Some do it in ways so strange they seem impossible. And one of them hides a surprise few people would ever expect. By the end of tonight, you're going to understand exactly how each world in our solar system would kill you, how long you would last on its surface, and why scientists are seriously planning to colonize the very places designed to destroy us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Imagine the surface appearing beneath you all at once. No gradual descent, no time to adjust. Just Venus, immediate and total. The air is not air. It is supercritical carbon dioxide, a state of matter that exists at extreme temperature and pressure simultaneously, neither gas nor liquid, but something between the two. Nothing like it occurs naturally on Earth outside a laboratory, and it is pressing against every square inch of your body with 92 times the force of Earth's atmosphere. The deepest a human being has ever descended in a pressurized diving suit is around 700 meters. You are already past the limit. You are past the point where the human body can survive. The pressure does not slowly compress you. It collapses you. Consciousness ends in seconds. But here's where it gets strange. The pressure is not even the primary problem. The temperature at the surface of Venus is 475 degrees Celsius, roughly 890 degrees Fahrenheit. A kitchen oven reaches perhaps 260 degrees at its maximum setting. Lead melts at 327 degrees. Tin melts at 232 degrees. Zinc melts at 420 degrees. Venus would melt all three. Leave a block of zinc on the surface of Venus and it turns to liquid. And the surface temperature barely changes between day and night, between equator and pole. The entire planet is wrapped in a uniform, relentless heat that never lets up and never cools. Venus is hotter than Mercury, despite being nearly twice as far from the sun. That fact stops people when they hear it for the first time. Mercury is a scorched rock with almost no atmosphere, exposed directly to solar radiation, and yet Venus runs hotter. The reason is the atmosphere itself. Carbon dioxide traps heat with extraordinary efficiency. Once the greenhouse effect took hold on Venus, the heat had nowhere to go. It built and built over millions of years, and now it simply stays. So what would it actually take to survive even briefly on that surface? Imagine the most advanced suit engineers could currently build. Titanium exterior plates for structural integrity. A silicon carbide outer layer rated to 500 degrees Celsius. A tantalum gold coating over exposed surfaces to resist sulfuric acid corrosion. Evaporative cooling systems cycling fluid against the heat. Internal oxygen recyclers and radiation shielding. This suit represents the outer edge of what materials science can currently offer. In it, you would survive approximately 20 minutes. Not 20 hours. 20 minutes. The failure sequence goes like this. For the first 10 minutes, the cooling systems fight. They are losing, but they are fighting. By the 10-minute mark, your core body temperature begins to rise despite the cooling. By 15 minutes, you are in severe heat stroke. The brain begins to swell. Organs start shutting down. By 18 minutes, the cooling systems fail entirely, overwhelmed by the environment. At 20 minutes, the structural integrity of the suit fails. The supercritical atmosphere floods in. That is the best case scenario for a human being on the surface of Venus. Now look up. Above you, The clouds extend from roughly 45 kilometers altitude to 70 kilometers. They move at 360 kilometers per hour. Lightning cracks through the toxic haze. The sky is a perpetual yellowish-orange twilight, thick atmosphere blocking most sunlight, the landscape below locked in a permanent murky orange gloom, like a sunset that never ends and never brightens. The Soviets went there anyway. Between 1961 and 1984, the Soviet space program launched more than 30 missions toward Venus. 10 landers successfully reached the surface. Every single one was destroyed, not gradually degraded, destroyed. The engineering challenge was so extreme that the Soviets essentially had to reinvent what a spacecraft could be. Thick pressure vessels, short operational windows, instruments designed to collect data and transmit it before the machine died. The longest any of those landers survived was 127 minutes. On March 1st, 1982, Venera 13 touched down on the Venusian surface. It sent back the first color photographs ever taken on another planet's surface, and it sent back something else. Sound. The first audio recording from another world. You can hear the rush of wind as the lander settles. You can hear the mechanical click as the lens cap ejects from the camera. And then you hear something harder to describe, a low grinding and shifting, the sound of an alien atmosphere pressing against Soviet steel. Then, the lander went silent. 127 minutes after arrival, Venera 13 is still there, on the surface of Venus. It has been there for more than 40 years. It is almost certainly unrecognizable by now. There is a related story that most people have never heard. In 1972, the Soviets launched a mission called Cosmos 482. The plan was to send a lander to Venus. The upper stage of the rocket failed, leaving the lander trapped in Earth orbit. It circled our planet for 53 years. Then, in May 2025, it finally came down. Parts of it almost certainly survived re-entry. The reason is that Cosmos 482 had been built to survive the surface of Venus. Its heat shielding and pressure vessel were engineered for conditions far more extreme than the atmosphere of Earth. A spacecraft that was meant to die on Venus instead fell back to Earth, still intact after half a century. Engineers at NASA's Glenn Research Center have spent years trying to understand what it would take to build something that could last longer than Venera 13 did. They constructed a facility called the Glenn Extreme Environments Rig, or GEER, which recreates Venus surface conditions inside a chamber on Earth. Temperature, pressure, atmospheric chemistry, all simulated at full scale. Electronics tested in that chamber have survived 21 days. That is not 21 days on Venus. That is 21 days in a simulated environment built to replicate Venus as precisely as current technology allows. It is still, by every measure, extraordinary. And it still does not tell us if a lander could survive 3 weeks on the real surface. Several missions are currently in development. ESA's Envision Orbiter, NASA's Da Vinci and Veritas missions, both delayed by budget constraints, and the Morning Star missions from Rocket Lab and MIT, with a potential launch window as early as 2026. Each of them is designed to reach Venus in a different way, from orbit, from probes descending through the clouds, from surface instruments that have to survive long enough to matter. None of them are certain. All of them are necessary. Because here is what we have recently come to understand about Venus. And it changes everything. The planet sitting 900 meters below survivability, the planet that melts zinc and destroys spacecraft in 2 hours, may once have been the most Earth-like place in the solar system. Geologists have identified what appear to be granite-like rocks on the Venusian surface. On Earth, granite does not form without liquid water. Liquid water is required for the geological processes that produce it. Climate models developed in the last decade suggest that Venus may have had surface oceans for somewhere between 2 and 3 billion years. 2 to 3 billion years. That is longer than complex life has existed on Earth. Then the greenhouse ran away. The oceans began to evaporate. As they did, water vapor entered the atmosphere, and water vapor is itself a greenhouse gas. More heat trapped, more evaporation, more water vapor. The cycle accelerated until the oceans were gone. The carbon that had been locked in ocean sediments was released back into the atmosphere as carbon dioxide. The temperature climbed to where it is now, and it stayed. not a dead planet from the beginning, a transformed one, a warning written in rock and heat. But the story does not end at the surface. At 50 kilometers altitude above the Venusian surface, something shifts. The temperature drops to between 30 and 70 degrees Celsius, roughly the range of a warm summer day on Earth. The atmospheric pressure at that altitude is approximately equal to Earth's at sea level. The gravity is nearly identical to what you feel standing on Earth right now. If you released a balloon filled with breathable nitrogen-oxygen air at that altitude, it would float, naturally, because breathable air is buoyant in carbon dioxide. A sealed habitat full of air would rise and stay aloft on its own. And the research emerging from those clouds has become, in recent years, genuinely difficult to explain. Ultraviolet absorption patterns in the upper atmosphere resemble organic compounds. Chemical disequilibria have been detected, meaning the atmosphere contains combinations of chemicals that should not coexist without something actively producing them. Iron and magnesium sulfates have been found in concentrations that are not fully accounted for by standard chemistry. And in 2020, astronomers announced the detection of phosphine, a gas associated with biological processes on Earth, in the Venusian clouds. That detection remains unresolved. The original signal has been contested and partially revised, but it has not been fully explained away. We do not know what is producing the ultraviolet absorption. We do not know what is maintaining the chemical disequilibria. We do not know what the phosphine signal means. Venus is a graveyard on its surface, and an open question above it, the fastest death in the solar system. And perhaps, somewhere in those clouds, something that has not died yet, and Venus is only the beginning. Move closer to the Sun, and the atmosphere disappears entirely. Venus has an atmosphere so thick, it behaves like an ocean. Mercury has almost nothing. A faint exosphere of scattered atoms, sodium, hydrogen, helium, oxygen, potassium, drifting at the edge of space, too thin to breathe, too thin to scatter light, too thin to stop anything coming from the Sun. You step from one extreme to the other. One planet defined by what its atmosphere became, the next defined by what it never had. Arrive on Mercury's night side and the cold hits first. The temperature here is around negative 73 degrees Celsius. That is colder than any winter ever recorded on Earth's surface. And yet it feels, in a strange way, almost survivable compared to what is coming. The landscape stretches out in long black shadows, craters, grey dust, fractured rock as old as the solar system itself. You could be forgiven for thinking you had landed on the moon. The terrain is nearly identical. The silence is the same. The darkness above is absolute, and the stars are there, sharp and perfectly still, because no atmosphere scatters their light. No shimmer, no twinkling, just hard points of white against black. But here is what is already happening, invisibly, to your body. Mercury has no magnetic field strong enough to deflect the solar wind. It has no atmosphere to absorb radiation. Everything that crosses the inner solar system arrives at Mercury's surface, unfiltered and unslowed. And on the night side, in the cold, in what feels like relative safety, the radiation is already at work. There are 3 forms of it, and each one operates differently. The first is galactic cosmic rays. These are not particles from the Sun. They are high-energy atomic nuclei, iron, oxygen, carbon, accelerated to near the speed of light by supernovae and violent events in distant galaxies. They travel through interstellar space and arrive from every direction at once. They can penetrate meters of solid rock. They pass through your suit, your skin, your organs, your DNA, leaving ionized trails of damage behind them. No practical shield stops them all. The second is solar particle events. During solar flares and coronal mass ejections, the Sun releases massive bursts of high-speed protons and electrons. A single unshielded solar particle event can deliver a lethal radiation dose in minutes, not hours, minutes. The third is ultraviolet radiation. Earth's atmosphere and ozone layer block the vast majority of the Sun's ultraviolet output. Mercury has neither. Every photon arrives at full intensity. All 3 are already crossing your body on the night side. The damage accumulates in a specific pattern. Radiation causes DNA double-strand breaks, points where the molecular ladder of your genetic code splits in 2. Repair enzymes exist for this. The human body handles a certain rate of damage, but the rate of damage on Mercury's surface exceeds the rate of repair. The breaks accumulate faster than they are fixed. The progression is nausea, vomiting, confusion, then bone marrow failure, then immune collapse, acute radiation syndrome. The night side does not kill you quickly, it kills you steadily, and then the sun rises. Mercury's solar day lasts 176 Earth days. When the sun clears the horizon, it does not set again for roughly 88 Earth days. That is 3 months of continuous daylight. And the sun, as seen from Mercury, is not the sun you know. From Earth, the sun occupies a small disk in the sky. From Mercury, at closest approach, it appears 3 times larger in angular diameter, a blinding white disk filling a much larger piece of the black sky, with no atmospheric filtering between it and your eyes. You would have seconds before retinal damage became permanent. Not minutes, seconds. The suit absorbs heat faster than it can shed it. External temperature climbs past 200 degrees Celsius, then 300, then 400. The dayside surface reaches 427 degrees Celsius, hot enough to melt lead, hot enough to melt zinc. The metals that hold civilization together become liquid on Mercury's ground. Cooling systems in any foreseeable suit design fail under that sustained thermal load. Researchers at Brookhaven National Laboratory and within NASA's Space Radiation Element Program have documented what chronic radiation exposure does at the low levels found in low Earth orbit: arterial stiffening, structural damage to the heart, long-term cardiovascular degradation. Mercury's dayside is not chronic, it is catastrophic. The survival window, once the sun is fully up, is approximately 15 minutes. Not a slow death, a rapid one. And yet, between 2011 and 2015, NASA's Messenger spacecraft orbited Mercury and returned something unexpected. In the surface imagery, scientists identified unusual features they called hollows, irregular depressions, collapse structures. Some appeared to be entrances to underground cavities. The leading explanation is lava tubes, channels carved billions of years ago by flowing magma, now drained and empty, preserved beneath the surface. We already know lava tubes exist on the moon. Some are large enough to contain entire cities. On Mercury, a lava tube as little as 20 meters below the surface would provide something the surface cannot: stability. The radiation that passes through everything above ground loses much of its penetrating power over even a short distance of rock. The temperature swings that range between -73 and +427 degrees Celsius on the surface become almost negligible underground. Micrometeorites that sandblast the surface constantly cannot reach the interior. A sealed structure inside a lava tube on Mercury would be protected from nearly every lethal mechanism the surface concentrates. Mercury is not a paradise underground. The gravity problem remains. At 38% of Earth's gravity, the human body begins to fail in slow motion. Bone density drops roughly 1 to 2% per month. Muscles weaken. The cardiovascular system, no longer working against full gravity to circulate blood, begins to decondition. Fluid redistributes toward the head and chest. A condition called spaceflight-associated neuroocular syndrome, SANS, reshapes the eyeball itself over months. Vision blurs. These are not acute crises. They are chronic ones. A colony underground on Mercury would still be a colony in slow physical decline, fighting the body's own adaptation to a world that is not Earth. And reaching Mercury at all presents a problem that most people do not expect. Mercury is the closest planet to the Sun. It should be easy to reach. It is not. In fact, it takes more energy to send a spacecraft to Mercury than it takes to send one to Pluto. The Sun's gravity well is the reason. To fall inward from Earth toward Mercury, a spacecraft must shed enormous amounts of orbital velocity. If it sheds too little, it slingshots past. If it sheds too much, it falls into the Sun. The Messenger spacecraft, launched in 2004, performed 6 gravity assists, looping around Earth once, Venus twice, and Mercury itself 3 times, gradually bleeding off velocity over 6.5 years before it could enter orbit. A mission to Pluto, at the far edge of the solar system, takes less fuel, because you're falling away from the sun rather than into it. Mercury is a radiation trap, with a logistical barrier and a tantalizing secret underground. Survival on its surface is measured in minutes. Survival beneath it might be possible. The hollows Messenger found are not confirmed lava tubes. They are possible lava tube entrances, collapse features, candidates. We do not know what lies beneath them, but the implication is clear enough. Mercury punishes everything that stands in the open. It rewards whatever learns to hide. And Mercury, for all its hostility, is still far from the most dangerous ground in the inner solar system. Further out means quieter danger. That is the intuition. Mercury punishes you in minutes, so further out should mean more time, more margin, more possibility. And in one narrow sense, that intuition is correct. Mars gives you more time. That is the problem. Imagine stepping onto the Martian surface at the equator on a summer afternoon. The temperature is plus 20 degrees Celsius. That is a comfortable spring day. The sky is a pale butterscotch pink, lit from a sun that hangs smaller and more distant than it does from Earth. Beneath your boots, rust-colored desert stretches in every direction. The horizon curves gently. You could look at this place and feel something close to recognition. It almost looks like a high desert on Earth. The light is softer, the colors are warmer, and the silence is total. But the silence is not peace. It is patience. The gravity is 38% of Earth's. An 80-kilogram person weighs roughly 30 kilograms here. Movement feels light, almost effortless. You push off the ground and hang in the air a moment longer than expected. For a few minutes, Mars feels like somewhere a human body could belong. That feeling is the first deception. The gravity is only 38% of Earth's, and nobody knows what that does to a human body over months or years. Astronauts aboard the International Space Station experience near zero gravity, and the data from those missions is unambiguous. Bone density falls 1 to 2% per month. Muscle mass shrinks. The heart, no longer working against full gravity to push blood upward, gradually loses mass and efficiency. Fluid shifts toward the head, increasing intracranial pressure. The eyeball itself changes shape. The optic nerve swells. Some astronauts return from 6-month missions with permanent vision changes. That syndrome has a name: Spaceflight Associated Neuroocular Syndrome, or SANS. Mars at 38% gravity is somewhere between Earth and the space station. Whether that middle ground is enough to prevent the worst effects is genuinely unknown. The experiment has never been run. There is no data point for long-duration human life at this gravity level. We simply do not know where the threshold is, or whether 38% clears it. But here is where it gets strange. Remove the suit, and the pleasant afternoon disappears in seconds. The atmosphere on Mars is 100 times thinner than Earth's. That single number changes everything. Breathable air requires pressure. Without pressure, the boiling point of water drops. At Mars' atmospheric pressure, water boils at a temperature lower than the surface temperature of a living human body. Remove the helmet, and the moisture on your tongue begins to vaporize. Your tears evaporate. The lining of your lungs begins to dry. Unconsciousness arrives in roughly 15 seconds. Your body does not explode. That is science fiction. What actually happens is quieter and worse. Soft tissues swell. Gas forms in the blood. Beyond recovery in roughly 90 seconds. The air you cannot breathe is 95% carbon dioxide. The remaining fraction is mostly nitrogen and argon. There is virtually no oxygen. You would not suffocate in the familiar sense. The body fails before that mechanism even begins. The suit keeps you alive, but the suit has limits. A Mars EVA suit gives it roughly 10 hours of life support before oxygen runs out and the CO2 scrubber saturates. 10 hours. That is the operational window for a single excursion outside the habitat. In those 10 hours, the dust tries to get inside everything. Martian dust is not like the dust on Earth. Earth dust is rounded. Rain, rivers, and ocean waves have tumbled it for billions of years, grinding the sharp edges smooth. Mars has had no rain for billions of years. The particles have never been tumbled. At a microscopic level, they are jagged, angular, shaped like tiny knives, and they are coated in perchlorates, chlorine-based compounds that are toxic to human biology. Perchlorates disrupt thyroid function. They interfere with iodine uptake. Prolonged exposure causes metabolic damage. In 2022, images from the Curiosity rover showed the rover's own wheels, made of aluminum, torn and punctured by the abrasive Martian soil over years of driving. What repeated contact with that material does to lung tissue is not a pleasant calculation. The dust embeds. It does not clear. The body cannot process it the way it processes ordinary particulates. Radiation reaches the surface without mercy. Mars lost its global magnetic field billions of years ago. The core cooled. The internal dynamo that generates a protective magnetic bubble shut down. Without that field, the surface is exposed directly to the radiation environment of space. The dose on the Martian surface is roughly 20 times higher than at Earth's surface. During a solar particle event, when the sun releases a burst of high-energy protons, that dose spikes further. A single major solar event could deliver the equivalent of years of normal exposure in a matter of hours. There is no warning system adequate to that threat. There is no faster route back inside if you are 40 minutes from the habitat on foot, and there is no rescue coming. Communication with Earth takes 4 to 24 minutes one way, depending on where both planets sit in their orbits. Send a distress call, and the earliest possible reply arrives nearly 10 minutes later. A coordinated emergency response from Earth is not a realistic option. Whatever happens on Mars, the people there will resolve it themselves, or not at all. NASA has a framework for assessing the risks of long-duration Mars missions. It is called RIDGE. The letters stand for radiation, isolation, distance, gravity, and environment. Mars hits every category, not one or two, all 5, simultaneously, continuously. And the temperature that felt so welcoming on arrival is not representative of the planet. The plus 20 degrees Celsius reading at the equator on a summer afternoon is a fleeting exception. By that same evening, the equatorial temperature drops to minus 70 degrees Celsius. At the poles, it reaches minus 150 degrees Celsius. The planet-wide average is minus 60 degrees Celsius. The warm afternoon is not a sample of Mars. It is a brief window in a single day in the most favorable location on an otherwise deeply cold world. In 2023, NASA ran a year-long simulation called the Chapeya mission at Johnson Space Center in Houston. 4 crew members lived inside a 1,700 square foot 3D printed habitat. They grew crops. They performed simulated EVAs. Communication with the outside world was delayed to match the actual Mars lag. The mission was designed to test every system. Technology held up. Food production held up. The limiting factor was psychology, isolation, confinement, the grinding monotony of a small enclosed space with the same small group of people. Day after month after month. The knowledge of being further from help than any human has ever been. That is Mars at its most honest. Venus kills in 20 minutes. Mercury in 15. Mars gives you roughly 10 hours per excursion, and then months, and then years. Enough time to build, enough time to grow food, and learn routines, and begin to feel at home. And enough time to feel the body changing in ways that cannot be reversed by a good night's sleep or a protein supplement. The danger on Mars is not the sharp shock. It is the slow, patient accumulation of everything the planet does to a living system that was never designed for it. Mercury rewards whatever learns to hide. Mars rewards whatever learns to endure. But endurance on Mars carries a cost that compounds quietly, day by day. And the full weight of that cost is something no human being has yet lived long enough to fully measure. But endurance has a cost, and Mars measures it slowly. Jupiter does not measure it at all. The moment you leave the inner solar system and arrive at Jupiter, the scale changes so completely that it feels like entering a different kind of universe entirely. Not a larger version of the rocky worlds you just left. Something categorically different. Jupiter is not a planet that happens to be very large. It is a failed star. Let that settle for a moment. Jupiter contains more matter than every other planet in the solar system combined. More than twice the combined mass of all the rest. And if it had been roughly 80 times more massive, the pressure and temperature at its core would have ignited hydrogen fusion. Jupiter would have become a star. The solar system would have been a binary system, 2 suns. And in a binary system, the gravitational dynamics that allowed Earth to form in a stable orbit at a stable distance, over billions of stable years, might never have emerged. You would not be here, not because of anything dramatic, because Jupiter fell short of a threshold by a factor of 80, and that shortfall is the reason you exist. The planet's diameter is 143,000 kilometers. Inside Jupiter, you could fit 1,300 Earths. The Great Red Spot, a storm raging continuously for at least 350 years, is larger than the entire Earth. Larger than the planet you were born on, just the storm. But the answer was stranger than expected. Jupiter's magnetic field is 18,000 times stronger than Earth's. It extends 7 million kilometers toward the Sun and stretches nearly all the way to Saturn's orbit in the other direction. And that field does not just sit there. It traps charged particles pouring in from the solar wind and from the constant volcanic eruptions of Io, one of Jupiter's moons, and it concentrates those particles into radiation belts of extraordinary intensity. Engineers who designed the Europa Clipper spacecraft describe Jupiter's radiation environment as the nastiest in the solar system. Each close flyby of Europa exposes the spacecraft to the equivalent of roughly 100,000 chest X-rays worth of radiation. The spacecraft carries a radiation vault, titanium walls lined with polyethylene and Kevlar, just to protect its instruments. And even then, flyby times are rigidly limited, because extended exposure would destroy the electronics regardless of the shielding. A human suit has nothing comparable, nothing close. The radiation alone would degrade your systems before you reach the cloud tops. Circuit boards would fail, sensors would give false readings, communication would cut out, you would be blind and deaf and already dying before you entered the atmosphere. But suppose you entered anyway. Suppose you crossed through the radiation belts intact. What would Jupiter's atmosphere actually do to a human being? On December 7th, 1995, a spacecraft named Galileo became the first and, to this day, the only vehicle to descend into the atmosphere of a gas giant. It entered at roughly 170,000 kilometers per hour and experienced 230 g of deceleration for about 2 minutes. A fighter pilot blacks out at 9 g. At 230 g, every bone in the human body shatters and every organ ruptures simultaneously. Galileo survived that entry because it was a sphere of titanium and beryllium engineered specifically for the task. It deployed a parachute, transmitted data for 58 minutes, descended approximately 87 miles into the atmosphere, and then fell silent, crushed, overheated, or both. A human body would not reach the transmission phase. In the upper atmosphere, ammonia clouds stretch across the sky in the white and tan bands visible in photographs. From the outside, those bands are beautiful. From inside, from underneath, they are a blinding toxic fog at temperatures around -100 degrees Celsius. Below that layer, ammonium hydrosulfide clouds, and then water ice clouds. Temperature rising, pressure climbing. The winds in Jupiter's jet streams sustain speeds over 370 miles per hour, and they shear from multiple directions simultaneously. The G-forces from wind shear alone would render a human unconscious, and then break the body apart. The lightning storms inside Jupiter produce bolts spanning over 600 meters, some of the most powerful lightning recorded anywhere in the solar system. Pressure builds, 5 times Earth atmospheric pressure, then 10, then 20. Temperature climbs past the boiling point of water, past 200 degrees Celsius, past 500. The suit compresses and heats simultaneously. At some depth, something unexpected happens. Hydrogen gas, under sufficient pressure, becomes liquid. You are no longer falling through an atmosphere. You are sinking through an ocean of liquid hydrogen with no surface below you and no sky above you that would allow return. Deeper still, thousands of kilometers below the cloud tops, liquid hydrogen does something that exists almost nowhere else in the universe. Under pressures so extreme there is no everyday comparison for them. Hydrogen begins to behave like a metal. It conducts electricity. It flows. This is metallic hydrogen, a state of matter barely reproducible in any laboratory on Earth. And this layer, this ocean of liquid metal, is what generates Jupiter's monstrous magnetic field. The same field that makes the radiation belts. The same radiation belts that kill electronics before you even enter the atmosphere. At the core, The pressure reaches approximately 25 million times Earth's atmospheric pressure. The temperature climbs to roughly 20,000 degrees Celsius, hotter than the surface of the Sun. Total estimated human survival time inside Jupiter, approximately 3 minutes. Probably less. Galileo lasted 58 minutes because it was not made of anything biological. Jupiter has no surface, nothing to stand on, nothing to colonize, but it has 95 known moons, and those moons are a different story. The 4 largest were first observed by Galileo Galilei in 1610. Io is the most volcanically active body in the solar system, its surface constantly remade by eruptions of sulfur and silicate lava, driven by tidal forces from Jupiter's gravity squeezing its interior. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and the only moon known to generate its own magnetic field. Callisto is ancient, its surface a cratered museum of the solar system's violent early history, nearly unchanged for billions of years. And then there is Europa. The surface of Europa is still, no wind, no weather, no sound except the hiss of oxygen in the helmet and your own breathing. The ice beneath your boots is so cold, roughly negative 150 degrees Celsius, that it does not behave like ice at all. It behaves like rock, dense, hard, locked. The ice extends downward approximately 20 to 35 kilometers, a shell of frozen water covering the entire moon. Beneath that shell is an ocean, a global ocean of salt water covering the entire surface of Europa from pole to pole, with no land anywhere. Its total volume is approximately twice the combined volume of all the oceans on Earth, possibly billions of years old, possibly not empty. You have about 15 minutes on the surface before you need to think about survival in a different sense than cold or vacuum. Europa sits inside Jupiter's radiation belts. The surface dose is approximately 540 rem per day. On Earth, the average person receives roughly 0.3 rem in an entire year. A lethal acute dose is around 400 rem. On Europa, a lethal dose accumulates in less than 18 hours. But that calculation is almost irrelevant, because electronics fail in minutes. Sensors give erratic readings. Communication systems die. Oxygen recycling malfunctions. You are not being poisoned slowly. You are being dismantled at the component level faster than any system can compensate. And something else was happening. The same radiation that is killing you is, simultaneously, creating breathable oxygen. Jupiter's charged particles slam into the surface ice of Europa and split water molecules apart. Hydrogen, too light for Europa's gravity to hold, escapes into space. Some of the oxygen stays. This process is called radiolysis, the splitting of chemical bonds by radiation. In 2023, NASA's Juno spacecraft made the first direct measurements of this process using an instrument called JADE. Europa generates approximately 26 pounds of oxygen every second through radiolysis, an ocean world producing breathable oxygen from its own frozen shell. And you are standing on top of it, suffocating inside a radiation storm, on a surface producing more oxygen per second than many biological systems on Earth. Not a dead moon, a chemically active one. Juno's instruments have told us something else. A 2025 study using Juno's microwave radiometer measured the ice shell thickness at approximately 29 kilometers, with an uncertainty of plus or minus 10. And within that shell, fractures and pores extend hundreds of meters downward, channels through which material might move between the surface and the deeper ice. The James Webb Space Telescope has detected something in Europa's chaos terrains, regions where the ice has been disrupted and refrozen, places called Tara Regio and Powys Regio, crystalline water ice, sodium chloride, ordinary table salt, carbon dioxide, hydrogen peroxide, the basic chemical ingredients for habitability, sitting on the surface, irradiated and waiting. But ice on the surface has no way to reach the ocean below on its own, or so it seemed. In January 2026, a study published in the Planetary Science Journal by researchers at Washington State University demonstrated that salt-rich ice on Europa's surface can become dense enough to sink, to drip slowly downward through the ice shell and, over approximately 30,000 years, potentially reach the ocean. 30,000 years sounds like a long time. Geologically, it is instantaneous. It means the surface chemistry, irradiated and reactive, has a delivery mechanism. The ocean is not isolated from the chemistry above it. It is receiving it. The ocean itself may have its own energy sources entirely independent of the surface. Even without hydrothermal vents on the ocean floor, radioactive elements in Europa's rocky core could be driving chemistry through the same process of radiolysis, radioactive decay splitting water molecules into chemically useful components. On Earth, microbial ecosystems have been found kilometers underground, in complete darkness, powered by exactly this mechanism. Uranium and thorium decay supplying the chemical energy. Life without sunlight, without photosynthesis, without any connection to the surface at all. Europa has an ocean. Salt, chemical energy from below, chemical ingredients delivered from above, and approximately 4 billion years of liquid stability in which all of this has been running. On Earth, life appeared almost as soon as conditions allowed. Almost as soon as liquid water was stable, something began. Not might have happened. Happened. The question for Europa is not whether the ingredients are there. They are. The question is whether 4 billion years was enough time for something to begin. And the honest answer is that we do not know. Not might not. Do not. On October 14th, 2024, a SpaceX Falcon Heavy rocket lifted off from Kennedy Space Center, carrying the Europa Clipper, the largest planetary science spacecraft NASA has ever built. It swung past Mars in February 2025, gaining velocity. It will pass Earth again in December 2026. It arrives at the Jupiter system in April 2030, carrying 9 science instruments inside a radiation vault designed to survive the same belts that would destroy an unprotected spacecraft in hours. Europa Clipper cannot orbit Europa directly. The radiation would destroy it too fast. Instead, it will orbit Jupiter and make 49 close flybys of Europa over the course of several years, dipping in and pulling back out, each pass collecting data on the ice shell, the ocean below, the surface chemistry, the magnetic environment. And there is one more possibility that has not yet been confirmed. Europa may be venting, water vapor pushing up through cracks in the ice, geysers rising as high as 120 miles above the surface. If they exist, Europa Clipper will fly directly through them. It will not need to drill through 29 kilometers of ice to reach the ocean. It will taste the ocean as it passes. Whatever that ocean contains, whether chemistry alone or something more, may be detectable from the outside. Jupiter is the planet that destroys, 15 minutes in its radiation belt, 3 minutes in its atmosphere, and sheltered in its gravity, drawing chemical energy from its radiation, receiving its own surface chemistry through its own ice, the ocean of Europa may have had 4 billion years to become something more than chemistry. That question is still open, and the answer may already be en route. Outward then, past the radiation belts of Jupiter, past the moon that may already hold an ocean of answers, farther from the sun than any of the worlds already covered. The outer solar system opens up here, and the next stop is the most beautiful planet ever photographed. Saturn hangs in space like something that should not exist. It is not simply a planet with rings. It is a visual impossibility, a banded golden sphere wrapped in a disk so thin and so vast that the geometry seems wrong. Saturn's diameter is roughly 9.5 times Earth's. It is, like Jupiter, a gas giant, hydrogen and helium all the way down, no solid surface to stand on, no ground beneath you at any depth. But the rings are their own revelation. They extend roughly 300,000 kilometers from the center of the planet. They are made of billions of individual pieces, chunks of ice and rock ranging from grains of sand to house-sized boulders. Each piece is orbiting Saturn independently, following the same laws of gravity that move the planets around the sun. And here is the thing about the rings that most people never quite absorb. They look like a flat disk, solid and permanent. They are not solid. They are not even close to solid. If you shrank Saturn down to the size of a football field, the rings would be thinner than a single sheet of paper. What looks from a distance like a glowing structure is almost entirely empty space. A cosmic illusion, drawn in ice. The auroras at Saturn's poles are worth a moment. They glow in ultraviolet and infrared, driven partly by Saturn's own magnetic field interacting with the solar wind, and partly by something unexpected. One of Saturn's inner moons, Enceladus, sprays geysers of water ice into space. Some of that material falls into Saturn's magnetic field and powers the auroras, a moon contributing to the light show of a planet 238,000 kilometers away. But descending into Saturn is not like admiring it from a distance. The atmosphere is moving, not slowly. Wind speeds in Saturn's upper cloud layers exceed 400 meters per second. That is roughly 1,300 feet per second. Earth's most powerful hurricanes reach winds of about 90 meters per second. Saturn is running more than 4 times faster, and the jet streams driving the bands reach over 500 meters per second. The yellow color you see in photographs comes from ammonia crystal clouds high in the atmosphere, shaped and sheared by those jet streams into Saturn's characteristic banded pattern. Temperature drops below negative 200 degrees Celsius almost immediately. Ice does not just accumulate on a suit in those conditions. It forms fast, sealing joints, frosting the visor, stiffening the insulation. The sideways winds at those speeds do not push, they impose. The turbulence inside a pressure suit would cause physical trauma on its own, the body being shaken by wind shear that changes direction as you pass through different atmospheric layers. Survival time in Saturn's atmosphere is approximately 5 minutes. Conscious perhaps 3. Saturn is not the destination. It never was. The destination orbits it. Saturn has 83 known moons. Most are small and frozen, geologically quiet, nothing more than captured rocks locked into orbit. But one of them is something else entirely. The second largest moon in the entire solar system, behind only Jupiter's Ganymede, larger than the planet Mercury. A world with weather, rivers, lakes, and a sky. That moon is Titan. Here is where the story changes. Every other world covered in this journey kills through a recognizable mechanism. Pressure, heat, cold, radiation, or atmosphere. Titan introduces a different problem, and it begins with something unexpected. Titan is the only moon in the solar system with a dense atmosphere. Not a trace atmosphere. Not an exosphere barely distinguishable from vacuum. A real atmosphere. The surface pressure on Titan is about 1.5 times Earth's atmospheric pressure at sea level. The composition is roughly 98% nitrogen, with traces of methane and hydrogen, chemically similar in structure to early Earth's atmosphere before oxygen became dominant. That pressure number has an implication that takes a moment to register. Not a pressure suit. You do not need one. A clothing breach on Titan means cold exposure, not explosive decompression. The air is thick enough that the pressure difference between inside your suit and outside is trivial. What you need is insulation, a heated inner layer to keep your core temperature stable, and an oxygen supply because Titan's atmosphere contains no breathable oxygen. But the rigid helmet, the pressurized joints, the bulky backpack of a full EVA suit, none of that is required. A kind of freedom of movement that exists nowhere else off Earth becomes technically possible on Titan. That is the surprise. Now comes the constraint. The temperature is negative 180 degrees Celsius. At that temperature, water ice is not ice the way we think of it. It is granite. It is bedrock. The surface of Titan is literally paved in frozen water that behaves like stone. Methane, normally a gas on Earth, is liquid on Titan. It fills lakes, flows in rivers, and falls from the sky as rain. And here is the paradox with the thick atmosphere. On the moon, or on the surface of Europa, cold loss happens primarily through radiation, the slow release of heat into vacuum. It is manageable. On Titan, the dense atmosphere conducts heat away from your body through direct contact, through conduction and convection. A thicker atmosphere means faster heat loss, not slower. The very thing that eliminates the pressure problem accelerates the thermal problem. Survival time on Titan before thermal systems are overwhelmed is approximately 2.5 hours. Within those 2.5 hours, you would be standing on a world with active weather. Methane rain falls from orange clouds in a golden, hazy sky. The sun is not visible as a disk from Titan's surface. The atmosphere scatters and diffuses the light until the sky glows amber, the same color in every direction. Rivers of liquid hydrocarbons have carved channels through water ice bedrock over millions of years. Those rivers flow into lakes and seas. Kraken Mare, the largest of Titan's hydrocarbon seas, is bigger than Earth's Caspian Sea. Ligeia Mare and Punga Mare are smaller, but still vast. Titan holds more surface liquid than any body in the solar system except Earth. And the volume of liquid hydrocarbons, the methane and ethane, represents hundreds of times more than all of Earth's known oil and natural gas reserves combined. Titan's gravity is 14% of Earth's. An 80-kilogram person weighs about 11 kilograms on Titan's surface. Think about what that means in combination with the thick atmosphere, low gravity, dense atmosphere. A human being, with wings strapped to their arms, could fly. Not metaphorically, not in a pressurized vehicle. A person generating their own muscle power could achieve sustained, human-powered flight on Titan in a way that is impossible on every other known world, including Earth, because Earth's gravity is too strong, over methane lakes, beneath an orange sky, with Saturn's pale rings arcing through the haze above. That flight is physically possible, but the biggest surprise on Titan was still coming. In 2025, NASA researchers including Christian Mayer and Connor Nixon published work describing what Titan's hydrocarbon lakes might be doing at the molecular level. The finding is not about temperature or pressure or gravity, it is about chemistry. And it changes the nature of the question we ask about Titan. Simple molecules in Titan's methane lakes can naturally form vesicles. A vesicle is a bubble-like compartment enclosed by a double-layered membrane. On Earth, vesicles are precursors to living cells. They are one of the first architectural steps in the sequence that leads from chemistry to biology. The mechanism works like this. Methane rain falling into a liquid hydrocarbon lake creates a spray of tiny droplets at the surface. Those droplets become coated by amphiphilic molecules, molecules with one end attracted to liquid methane and one end repelled by it. The same general principle operates in water-based chemistry on Earth, where it drives the formation of cell membranes. When a coated droplet falls back into the lake, it picks up a second layer, 2 layers, a bilayer membrane, a vesicle. Over time, the more stable vesicles persist. The less stable ones break apart. The chemistry is selecting for stability, natural selection at the chemical level, no biology required, just thermodynamics, filtering structures by their durability. That is the architecture life uses, assembling itself, possibly right now, in lakes of liquid methane 1.4 billion kilometers from Earth. The research did not stop with vesicles. Also in 2025, a team from Charles University working with NASA published findings in the Proceedings of the National Academy of Sciences about a different molecule in Titan's chemistry. Hydrogen cyanide, or HCN, a compound critical to the formation of amino acids and nucleobases, the building blocks of proteins, and DNA. The study found that HCN can form stable crystals with methane and ethane under conditions present on Titan. This breaks what chemists call the like dissolves like rule, the principle that molecules mix with similar molecules and not with dissimilar ones. HCN should not be stable in Titan's hydrocarbon environment. It is. The chemistry of Titan is not following the expected rules. We do not yet know whether any of this leads to life. The vesicle formation is a proposed mechanism, confirmed by modeling and laboratory work, not yet observed directly on Titan's surface. The HCN crystal behavior is real and measured, but whether it proceeds further into prebiotic synthesis, whether it eventually produces something that replicates, that is still an open question. NASA's Dragonfly mission will not answer it completely. Dragonfly is a rotorcraft that will fly through Titan's dense atmosphere and land at multiple surface sites, studying chemical composition and atmospheric chemistry in detail. It will not land on the lakes directly, but it will provide the first ground truth measurements of Titan's chemical environment from the surface itself. And those measurements will either support or constrain the vesicle and HCN hypotheses. What Dragonfly may find is a moon where the chemistry of life's first steps is playing out in a completely different solvent, in a completely different cold, under a completely different sky. Two things coexist on Titan in a way that exists nowhere else. A surface where a human being, wearing insulated clothing and carrying an oxygen supply, could walk and could fly with their own wings over liquid methane lakes. And in those lakes, the molecular architecture that biology uses to begin may already be assembling itself, not as a product of life, as a predecessor to it. The same moon, the same orange sky, and somewhere beneath it, the question of whether life requires water at all may already be in the process of being answered. That question will not stay abstract much longer, but Titan is behind you now. The orange fades, the methane lakes recede, and the further out you travel, the more the sun changes. Not in color, in size. It shrinks. Past Saturn, past the distance where its warmth ever reached the surface of anything, the sun becomes something you remember rather than something you feel. It is still there, a bright point of light in a black sky, brighter than any star, but no longer a disk, no longer a source of heat you could ever measure on your skin. Out here, the cold is not a side effect. It is the environment itself. Uranus sits 2.9 billion kilometers from the sun. Light leaving the sun this moment will take 2 hours and 40 minutes to reach it. When it arrives, it brings almost no warmth. The planet is tilted at 98 degrees, which means it essentially rolls along its orbit on its side. The poles take turns pointing almost directly at the sun. For roughly 42 Earth years at a stretch, one pole sits in continuous sunlight. Then the planet rolls, and it switches. The leading theory is that something enormous, an object roughly the size of Earth, struck Uranus early in the solar system's history and knocked it over. No one knows for certain, but the evidence is in the tilt, and the tilt is unmistakable. You would not survive long enough to observe any of this. At Uranus, the winds reach 560 miles per hour. The temperature is minus 220 degrees Celsius. Your suit's thermal systems would be overwhelmed within minutes. There is no surface to land on. Hydrogen gas transitions downward into hot, dense fluid. Deeper still, a slurry of water, ammonia, and methane exists under pressures that would compress any known material. You would fall through layers of atmosphere, losing heat faster than any technology could replace it, until your core temperature dropped below 30 degrees Celsius. At that point, ventricular fibrillation begins. The heart stops coordinating. Survival time on Uranus is 3 to 5 minutes, but the reality was different. Deep inside Uranus, and likely inside Neptune as well, something may be raining down through the interior. Carbon atoms, subjected to the pressures and temperatures found tens of thousands of kilometers beneath the cloud tops, may be compressed into diamonds. Actual diamonds, forming continuously, sinking slowly through the dense fluid interior, accumulating at the core. We do not know for certain. The pressures involved are difficult to replicate in any laboratory on Earth, but the physics suggests it is possible, and experiments at lower scales have shown carbon behaving exactly this way under analogous conditions. Inside these cold, dim giants, one of the most valuable substances on Earth may be as common as rain. Uranus has 27 known moons. The largest, Titania, is about half the size of Earth's own moon. Gravity on Titania is low enough that an 80-kilogram person would weigh about 4.5 pounds. Oberon, Umbriel, Ariel. Each world is geologically quiet, cold, and ancient. Then there is Miranda. Miranda looks like it was shattered and reassembled by someone who lost the instructions. Its surface is a chaotic patchwork of canyons, cliffs, ridges, and plains that do not match each other. Ancient terrain runs directly against young terrain. Cliffs drop 20 kilometers, some of the tallest known in the solar system. The leading hypothesis is that Miranda was struck hard enough to break apart, and the pieces reassembled in the wrong order. On Miranda, you would weigh just over 2 pounds. A jump that felt casual would carry you meters into the air. Move too quickly, and you would drift off the surface entirely. Miranda is not a place you could comfortably stand on. It is a place you would have to navigate carefully, holding onto things, watching every movement, aware that the gravity barely has you. Neptune is further still, 4.5 billion kilometers from the sun. Sunlight takes more than 4 hours to reach it, and Neptune is where the solar system reaches its most violent atmosphere. The winds on Neptune are the fastest measured on any planet. On August 25th, 1989, Voyager 2 flew past Neptune and measured wind speeds of 1,300 miles per hour. That is 5 times the speed of sound. Neptune receives far less solar energy than Jupiter or Saturn, by every model scientists had built before Voyager 2 that should have meant a quieter atmosphere. It did not. It had one of the most dynamic weather systems ever observed. No one could fully explain why. The internal heat Neptune generates, some residual warmth from its formation, appears to drive circulation that the Sun alone cannot account for. The mechanism is still not completely understood. The Great Dark Spot was a storm the size of Earth, an anticyclonic system with winds exceeding 2,300 kilometers per hour at its edges. Voyager 2 photographed it in 1989. When the Hubble Space Telescope looked again in 1994, the Great Dark Spot was gone. A new one appeared elsewhere on the planet later. These storms form and dissolve on Neptune in ways that have no parallel in the solar system. Survival time on Neptune is less than 2 minutes. Not because the cold overwhelms the suit first, because the wind tears the suit apart before the cold finishes the job. The atmosphere is hydrogen, helium, and methane. The wind is the lethal mechanism. Neptune has 14 known moons. The largest is Triton, and Triton is one of the strangest objects in the solar system. It orbits Neptune backward, not slightly tilted, retrograde, moving in the opposite direction of Neptune's rotation. Almost every large moon in the solar system orbits in the same direction as its planets spin, because they formed from the same rotating disk of material. Triton did not form this way. It was almost certainly captured. Neptune's gravity pulled it in from elsewhere, likely from the region beyond the planets, the cold belt of objects where Pluto lives. The capture would have distorted Triton's orbit for millions of years, generating enormous tidal heat before the orbit gradually circularized into what it is now. Triton's surface is frozen nitrogen, with pinkish organic deposits scattered across it, and it is not geologically dead. Nitrogen gas geysers shoot dark particles 8 kilometers into the sky, driven by solar heating of the transparent frozen nitrogen surface. The Sun, from Triton, is just a bright star, but even that faint energy is enough to sublimate the nitrogen beneath the surface, building pressure and releasing it upward in plumes you could see from a spacecraft. A captured world, orbiting backward with active geysers in the outer darkness of the solar system. Not a dead moon, a restless one. Voyager 2 is the only spacecraft ever to visit Neptune. It flew past on that August day in 1989, spent a matter of hours in close proximity, and then continued outward. It is now in interstellar space, still transmitting, a whisper from the edge of everything we know. No mission has returned. Neptune remains, in almost every meaningful sense, a world we visited once, briefly, and have not been back to. Beyond Neptune, where the solar system's gravitational reach finally begins to fade, is Pluto. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet. The definition of planet had been debated for years, and Pluto, orbiting in a region crowded with similar small icy bodies, did not meet the new criteria. The reclassification was controversial. It remains so, but the object itself did not change. On July 14th, 2015, after a journey of 9.5 years, NASA's New Horizons spacecraft flew past Pluto. What it sent back changed what most people thought they knew about the edge of the solar system. Pluto has mountains of water ice rising 3,500 meters above vast plains of frozen nitrogen. The mountains are geologically young by planetary standards, suggesting that some internal process reshaped the surface relatively recently. There are nitrogen ice glaciers moving slowly across the landscape, fed by the plains. There is a heart-shaped feature visible from space, a broad nitrogen ice basin that caught the attention of everyone who saw the first images. Pluto has a thin atmosphere of nitrogen, methane, and carbon monoxide that partially collapses when its long, elliptical orbit carries it farther from the Sun, causing the atmosphere to freeze and fall to the surface. When it approaches closer, the atmosphere rebuilds itself. Pluto breathes slowly over the course of its 248-year orbit. The surface temperature is at minus 220 degrees Celsius. The Sun is a bright star, nothing more. Sunlight takes over 5 hours to arrive. Gravity is 6% of Earth's, so a gentle jump carries you meters into the air and brings you back down slowly. The silence is absolute. There is no wind you would feel, no weather in any conventional sense. Survival on Pluto is approximately 8 minutes, not because of radiation, which is minimal, not because of wind. The cold makes the materials of a suit brittle. A seal that would hold in warmer environments cracks. At minus 220 degrees Celsius, exposure is not gradual. It is immediate. 8 minutes. On a world that took 9.5 years to reach. A world with mountains and glaciers, and a seasonal atmosphere and a heart drawn in frozen nitrogen across its surface. That combination sits with you differently than the others. Mercury kills in minutes with radiation and heat. Venus dissolves everything in seconds. Jupiter disassembles you with pressure and cold in 3 minutes. Neptune's winds tear the suit in under 2. Pluto simply waits, coldly, quietly, patiently, and the beauty of it makes the waiting stranger. The outer solar system has not finished its surprises, but its purpose here has. We have crossed every world, measured every threat, and arrived at the same conclusion every time. None of them will sustain us. Not one. Neptune ends you in under 2 minutes. Mars, the friendliest option in the solar system, gives you roughly 10 hours before the oxygen runs out, and the suit's scrubbers saturate. 10 hours is the slowest death on offer. And yet, that gap matters enormously, because 10 hours is time enough to think, time enough to build, and somewhere inside that gap, a plan has taken shape. Humanity is not waiting. This is not a thought experiment or a distant aspiration. There are rockets. There are budgets. There are engineers working today on the problem of leaving this planet for good. The question has shifted from whether we will go to when, and at what cost, and who will go first. The vehicle at the center of that plan is unlike anything built before. SpaceX Starship, when fully assembled atop its super heavy booster, stands 122 meters tall. That is taller than the Statue of Liberty, taller than the Saturn V, the rocket that carried humans to the moon. The numbers on what sits beneath it are difficult to absorb. Super Heavy carries 33 Raptor engines. At liftoff, those engines generate approximately 74 meganewtons of thrust. That is nearly twice the thrust of the Saturn V. The upper stage adds 6 more Raptor engines. In its expendable configuration, Starship is designed to carry 150 metric tons to low Earth orbit. For context, the Saturn V carried about 130 metric tons. Starship is bigger, heavier, and built to be reused. That last word is the key. Reusability is the holy grail of rocketry. Every rocket that has ever launched has been, in economic terms, a catastrophic waste. You build an enormously complex machine, burn it into the sky, and it falls into the ocean. You build another one. Starship is designed to end that cycle. The Super Heavy booster launches, accelerates Starship to roughly 8,650 kilometers per hour, detaches, flips itself around, and flies back to the launch site, where mechanical arms catch it midair. The first time that catch was successfully demonstrated was Flight Test 5. It looked impossible. A booster the size of an office building, snatched from the sky by what looked like a giant pair of chopsticks. But the picture did not hold. That Flight Test 5 moment, as dramatic as it was, came inside a track record that tells a more complicated story. As of late 2025, Starship had completed 11 fully integrated test flights. 6 were successful, or mostly successful. 5 ended with significant failures, explosions, loss of vehicle, or mission objectives not met. And across all 11 flights, Starship had never fully reached orbit. Every test flight has been suborbital. The vehicle that is supposed to carry humans to Mars has not yet completed an orbital mission. That caveat matters because the timeline depends on it. In September 2024, SpaceX announced an extraordinary plan. 5 uncrewed Starships would launch toward Mars during the 2026 transfer window, carrying Tesla Optimus humanoid robots and autonomous construction equipment. If those missions succeeded, crewed flights would follow in the 2028 window. The Earth-Mars alignment that allows efficient transfer occurs roughly every 26 months. Miss a window, and you wait more than 2 years for the next one. The 26-month constraint is not a preference. It is orbital mechanics. It does not negotiate. By May 2025, the picture had already shifted. Elon Musk acknowledged the 2026 timeline was ambitious. He estimated the odds at about 50-50. The bottleneck was not the rocket itself. It was orbital refueling. Each Mars-bound Starship would need approximately 12 tanker launches to fill its propellant tanks in orbit before departing for Mars. 5 Starships in a single departure window would require roughly 60 tanker launches, all within a narrow interval. SpaceX had not yet demonstrated orbital propellant transfer between 2 Starship vehicles. Not once. The system that the entire Mars plan depends on had never been tested in the environment where it would need to work. Then came February 2026. Musk announced that SpaceX would deprioritize Mars for approximately 5 to 7 years. The focus would shift to lunar missions. SpaceX holds a roughly $3 billion NASA contract for the Artemis lunar lander. The moon offers a shorter return on investment, closer logistics, and a faster path to proving the technology. The 2026 Mars window will pass unused. The 2028 crewed window is now unrealistic. Expert consensus has settled around 2035 to 2040 for the first human Mars landing, nearly a decade later than the plan announced just months before. What has not changed is the architecture of how it would work when it finally happens. The plan unfolds in 3 phases, and the logic of each phase depends on the one before it. Phase 1 is robots. Uncrewed starships arrive first. They carry Tesla Optimus humanoid robots and autonomous construction equipment. The robots deploy solar panels, locate water ice deposits beneath the Martian surface, and begin preparing infrastructure before any human steps off a ship. It is a sound concept. It is also worth being honest about where it stands. Optimus demonstrations to date have been partially remote controlled. Its ability to operate autonomously in the unstructured, unpredictable environment of the Martian surface is unproven. The concept itself is not new. NASA has planned robotic site preparation architectures for Mars missions for decades. The technology to execute it does not yet fully exist. Phase 2 is cargo. More than 20 starships arrive in the next transfer window, each carrying 75 metric tons of payload, habitats, life support systems, power generation equipment, and the hardware for something called In Situ Resource Utilization, or ISRU. ISRU is the process of making what you need from what Mars has. The Martian atmosphere is 95% carbon dioxide. The Martian subsurface holds water ice. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water. Electrolyze that water and you recover hydrogen and oxygen. The methane and oxygen become rocket propellant. You make the return ticket from Martian air and Martian ice. Without ISRU, there is no return trip. The physics of carrying enough propellant from Earth make the math impossible. With ISRU, the depot refills itself from the planet around it. Phase 3 is the one that changes everything. The first crewed starship arrives. A small crew steps into robot-prepared habitats. They grow food in pressurized greenhouses. They conduct surface operations in suits with a 10-hour window each time the airlock opens. They are the first humans on another planet. What they live inside has become its own area of serious engineering. NASA's 3D printed habitat challenge produced the Mars Ice House, a 4-story translucent igloo constructed from Martian water ice. The same ice that the habitat is built from shields against radiation. The structure that keeps you alive also absorbs the energy trying to kill you. In July 2025, a study published in the journal Science out of Harvard took the idea of habitat further. Researchers developed bioplastic habitats made from polylactic acid, a plant-derived biodegradable material. Inside the walls of these structures, green algae survived under Mars-like conditions. The algae photosynthesized. They produced oxygen. The habitat wall became a living system. The habitat grows. The habitat repairs itself. The habitat breathes. That is genuinely new. A structure that participates in keeping its occupants alive, not just passively, but biologically, is a different kind of engineering than anything yet deployed in space. None of this makes Mars easy. Real, funded, and being actively engineered does not mean solved. Radiation has no complete solution. Low gravity at 38% of Earth's has no solution short of spinning the habitat, which no one has built at this scale in space. The psychological challenge of permanent isolation, cut off from Earth by a communication delay of 4 to 24 minutes one way, has never been tested at the duration and distance Mars would require. First-generation conditions on Mars will be more austere than any Antarctic research station on Earth, and those stations have emergency evacuation options that Mars will not. The plan is internally coherent. The engineering is extraordinary, and it is behind schedule in ways that decades of space exploration suggest are normal. The biggest surprises in this story are still ahead. But Venus is not finished with us yet. We left it behind early. We measured how fast it would kill us on the surface, counted the seconds the Soviets managed to keep their machines alive, and moved on to worlds that offered more time. Mars gave us 10 hours. Mercury gave us 15 minutes on the day side. Even Pluto offered 8. Venus gave us 20 minutes before the pressure alone would have begun to win. And that was before the heat, before the acid, before the air that is not air. But the reading came back reversed. We have been thinking about Venus wrong. Not the surface, 50 kilometers above it. At 50 kilometers altitude, the temperature drops to somewhere between 30 and 50 degrees Celsius, 86 to 122 degrees Fahrenheit. Warm, certainly. Uncomfortably warm on a bad day, but survivable. The pressure at that altitude is approximately 1 bar. Earth sea level. The same pressure you are breathing right now. Gravity runs at 90% of Earth's. You would feel it as a very slight lightness, nothing more. Think about what that means. We have now visited Mercury, Mars, the Moon in context, Jupiter, Saturn, Titan, Uranus, Neptune, and Pluto. Not one of them offers those 3 conditions simultaneously. Not one. The upper atmosphere of Venus, the planet that kills faster than any other, is the most Earth-like environment in the entire solar system, beyond Earth itself. More Earth-like than Mars. More Earth-like than any moon of Saturn or Jupiter. More Earth-like than anywhere else we have gone. The catch is the 50 kilometers of nothing below you. But here is the elegant solution, and it is genuinely elegant. Venus's atmosphere is almost entirely carbon dioxide. CO2 is a heavy molecule. A nitrogen-oxygen mix, ordinary breathable air, is significantly lighter than CO2 at the same pressure and temperature. A sealed container filled with the air you breathe would float naturally in Venus's atmosphere. No hydrogen, no helium, no separate lifting gas at all. The lifting gas and the living space are the same thing. People would live inside the thing that makes it fly. The habitat does not need to generate lift. It is buoyant by nature, the way a sealed air pocket rises in water. And because the pressure inside and outside would be nearly equal, a puncture would not mean catastrophe. Air would leak slowly, not explosive decompression, not instant death. A slow leak that gives time to find and fix the problem. NASA has a reference design for exactly this concept. It is called HAVOX, the High Altitude Venus Operational Concept. The reference airship runs 129 meters long and 34 meters high, roughly the size of a football field, but tall. The outer skin is treated to resist sulfuric acid. Solar panels cover the upper surface, and that solar advantage is real. Venus receives approximately 1.9 times the solar flux that Earth does. Solar power on Venus is nearly twice as efficient as on Earth. The engineering case for a cloud habitat is not wishful. It is a serious design study from serious engineers. There is more. Venus is closer to Earth than Mars. At closest approach, Venus sits roughly 38 million kilometers away. Mars, at its closest, is around 55 million kilometers. Venus alignment windows for launch occur more frequently than Mars windows. A crewed mission to Venusian orbit, and eventually to a cloud habitat, would take less time and launch more often than an equivalent Mars mission. The solar system's most hostile surface turns out to orbit closer and cheaper than the world we have been planning to colonize for decades. The challenges are real, and they deserve honesty. Sulfuric acid at altitude is not a trace contaminant, it is pervasive. The material science for keeping a structure acid-resistant over years or decades remains unsolved. There is no solid ground. Everything floats. A drop tool does not land 3 feet away. It falls 50 kilometers into a furnace. It is gone. Resupply, construction, manufacturing, food production, everything that a colony needs to do with its hands must happen while floating, with no surface to push against. Wind at habitat altitude runs around 360 kilometers an hour. The atmospheric cloud level super-rotates, meaning it circles the planet much faster than the surface below it rotates. The Venusian solar day is 243 Earth days. The atmospheric cloud altitude completes a full lap of the planet in approximately 4 days. A floating habitat would circle Venus every 4 Earth days, carried by the wind whether it wanted to be or not. But here is the consequence that no one immediately expects. That circulation gives the habitat a sunrise roughly every 48 hours. Not 243 Earth days of unbroken day, not 243 days of unbroken night. A near Earth-like day cycle, created entirely by the wind, arriving for free, built into the planet's own atmospheric physics. Now comes the part that connects Venus to something much larger. Venus and Earth form from the same cloud of gas and dust, approximately 4.5 billion years ago. They are nearly identical in size, mass, and density. For billions of years, they may have looked similar from the outside. Venus may have had liquid oceans for 2 to 3 billion years. Rocks on Venus bear signatures consistent with granite formation, and granite requires liquid water. The surface of Venus was not always a furnace. Something went wrong. The greenhouse effect ran away, possibly hundreds of millions of years ago, possibly as recently as 700 million years ago. Oceans evaporated. Water vapor trapped more heat. CO2 released from rocks into the atmosphere. More CO2 trapped more heat. Each step made the next step worse, and there was no mechanism left to reverse it. Here is the fact that matters. Earth and Venus have roughly the same total amount of carbon. On Earth, most of that carbon is locked in rocks, in limestone, shale, coal, and petroleum. On Venus, all of that same total carbon is in the atmosphere as carbon dioxide, wrapped around the planet. The difference between a habitable world and a furnace is not the amount of carbon. It is where the carbon sits. Venus is not a warning that Earth will inevitably follow. The physics differ. Earth's distance from the sun, the water cycle, the stabilizing feedbacks built into the climate system, all of these make the same runaway sequence far less likely here. But Venus shows with absolute clarity what happens when those feedbacks fail. It is a data point about the fragility of the conditions that make a planet livable, written in sulfuric acid and 475 degrees of heat. And then, there is the question the scientists cannot quite answer yet. A 2025 peer-reviewed review examined the evidence for biological activity in Venus's cloud layer. The findings were careful and unsettling. Ultraviolet absorption patterns in the clouds resemble organic compounds. Chemical disequilibria exist in the atmosphere that are difficult to explain through non-biological chemistry alone. Iron and magnesium sulfates appear in the cloud layer. Solar radiation at cloud altitude provides enough energy to support photosynthetic processes. Wait, photosynthesis. In the clouds of Venus? The COSPAR assessment from 2023, the Committee on Space Research, placed limits on that idea. The clouds are orders of magnitude drier and more acidic than the survival limits of any known life on Earth. The uncertainty in exact water content and pH measurements at cloud altitude is significant. Known life cannot survive there, not by any margin we can currently measure. But known life evolved on Earth. It did not evolve in sulfuric acid clouds. The question is whether something else might have. If Venus once had oceans, and life appeared in those oceans, and that life had 2 to 3 billion years to adapt before the surface became hostile, some fraction of it might have migrated upward, into the clouds, developing membranes resistant to sulfuric acid, metabolisms built around chemistry that Earth life never needed to try. We do not know. We cannot know from a distance. The Morning Star missions, developed at MIT with Sarah Seeger leading the scientific effort, are designed to begin answering that question. A probe descends through the Venusian atmosphere, collecting direct samples of cloud chemistry, searching for complex organic molecules. It will not find definitive proof of life. That would require a follow-up mission capable of doing more, but it will return the first direct chemical sample from the altitude where those UV anomalies live, where those disequilibria exist, where the evidence is ambiguous in exactly the way that makes scientists unwilling to dismiss it. Venus killed us in 20 minutes on the surface. 50 kilometers up, it offers the most Earth-like conditions in the solar system. And somewhere in those clouds, suspended in acid, carried by 360 km/h winds, orbiting the planet every 4 days, there may be something we have not yet found the language to describe. The question of what lives in the clouds, if anything does, will not stay open much longer. The question of what Venus holds in its clouds may not stay open much longer. But that question belongs to a world close enough to watch from Earth with the naked eye. The next world we need to consider is much farther out, much colder, much harder to reach, and in ways that take time to appreciate. Far more livable than anything we have visited so far. Titan sits roughly 900 million kilometers from Earth. At its fastest, a spacecraft takes 6 to 7 years to get there. A message sent from a Titan colony arrives on Earth more than 70 minutes after it was sent. A reply arrives more than 70 minutes after that. By the time Earth knows something went wrong, the people on Titan have already been dealing with it for over an hour. Titan is, in every practical sense, beyond rescue, beyond resupply on short notice, beyond the kind of real-time support that kept early space missions alive. And yet Titan has something no other world in the outer solar system can offer. It has everything you need. The atmosphere alone changes the equation. The air on Titan is roughly 98% nitrogen, with traces of methane and hydrogen. It presses down at 1.5 times Earth's sea level pressure. That means a human standing on Titan's surface does not need a pressurized suit. The joints do not need to be rigid. The seals do not need to hold against the vacuum. A breach in the outer layer of your clothing means you are cold. Not dead, not instantly incapacitated. Cold. Insulated clothing, a heated inner layer, and an oxygen mask are enough. That is closer to cold weather gear than to a spacesuit. No world we have visited so far has offered anything like it, but something else was happening. The atmosphere that makes Titan feel accessible is also what makes the radiation picture completely different from anything else in the outer solar system. Saturn's magnetosphere deflects the charged particles that make Europa's surface lethal within 15 minutes, and that steadily damage tissue on Mars. Titan sits within that magnetosphere most of the time. On top of that, Titan's thick atmosphere absorbs the cosmic rays that would pass straight through Mars's thin one. The result is that radiation on Titan is not a significant concern. Safer than Mars. Safer than the surface of the Moon. A colonist on Titan faces cold and distance and gravity. Radiation is not on the list of daily threats. The energy picture is equally striking. The surface and shallow subsurface of Titan are saturated with hydrocarbons. Methane and ethane fill lakes and seas in liquid form. Solid organic compounds coat the surface like tar. Kraken Mare, the largest of Titan's seas, holds more hydrocarbon fuel than all of Earth's proven oil and natural gas reserves combined. And that is one lake. The total hydrocarbon inventory across Titan is estimated at hundreds of times everything fossil fuels ever gave us. A colony would not be rationing fuel, it would be swimming in it. The oxygen problem is real, but solvable. Titan's atmosphere carries no oxygen. None. But water ice is everywhere just beneath the surface. Titan's crust is essentially water ice, frozen hard as granite at negative 180 degrees Celsius. You drill down, collect ice, melt it, and run an electric current through the water. That process, electrolysis, splits water into hydrogen and oxygen. The electricity to run electrolysis can come from burning methane with the oxygen you just produced, from nuclear reactors, or from wind turbines turning in Titan's thick, dense air. The oxygen problem solves itself from the ice under your feet. And then there is flying. Titan's gravity is 14% of Earth's. An 80-kilogram person becomes an 11-kilogram person. The moon's gravity is 16.5% of Earth's, and no one can fly on the moon. But Titan's atmosphere is denser than Earth's. That combination is what matters. The lift required to become airborne drops to a fraction of what Earth demands. The thick air gives wings something real to push against. The result is that a human with lightweight wings and working leg muscles can achieve powered flight on Titan. A running start, flap, soar out over methane lakes beneath an orange haze. It is not a metaphor. The physics work. A Cessna designed for Earth, with no modifications, would fly on Titan, not struggle, fly. The same dense atmosphere and weak gravity that enable flight also enable other things. Boats could sail the methane seas. Saturn's tidal forces create tidal changes of roughly 1 meter in Krakenmare. That is enough for hydroelectric generation. Wind turbines at altitude could produce hundreds of megawatts. Titan offers energy in more forms than any colony could need. The habitats would be inflated domes, double-walled for insulation, partially buried in Titan's ice crust for thermal mass, warm nitrogen and oxygen inside, Earth normal pressure, lighting, room to move. A colonist steps through a lock into the cold in insulated clothing, and a respirator does what needs doing outside, and steps back into a building that feels, for all practical purposes, like home. The nitrogen to inflate those domes comes from the air. The oxygen and hydrogen come from the ice. The plastics and structural materials come from the hydrocarbons coating the surface. A Titan colony can be largely self-sufficient in ways a Mars colony cannot match. Mars is cold and thin and nearly empty of useful chemistry. Titan is saturated with it. None of this makes Titan easy. The challenges are real and they are serious. Distance means that resupply must be planned half a decade ahead. Anything that breaks must be fixed with what is on hand. That is not a short-term logistical problem. That is the structure of life. Gravity causes its own slow damage. 14% of Earth's gravity means the same bone loss, muscle atrophy, and cardiovascular degradation that every long-duration space environment produces, but without the option of returning to Earth to recover. A permanent colony on Titan needs centrifuges, rotating habitat sections where colonists spend hours each day under simulated gravity, sleeping in a slowly rotating drum to give the body what the planet cannot. The engineering for this at colony scale does not yet exist. Cold attacks every mechanism. Lubricants freeze, metals become brittle, plastics crack. Every system that operates outside a heated enclosure must be designed for conditions far past anything routine engineering handles. The materials science for sustained cryogenic operation on Titan is not where it needs to be. But consider what Titan offers in return. Abundant fuel, low gravity, a relatively low escape velocity. A colony at Titan could manufacture methane and liquid oxygen from local resources and load it into outbound ships. A spacecraft refueled at Titan could continue outward into the deep solar system, carrying a fraction of the mass it would need if it carried fuel from Earth. Titan becomes a waypoint, a depot, a truck stop on the highway to the stars. NASA's Dragonfly mission will provide the first real data. A car-sized rotorcraft will land at multiple sites across Titan's surface, analyze composition, map atmospheric chemistry, and search for prebiotic chemical complexity in the methane lakes. It will not tell us everything, but it will give us ground truth for the first time. Dragonfly is the beginning of knowing Titan rather than only imagining it. The biggest discoveries, though, may not be on the surface at all. Europa killed us in under 15 minutes from radiation. We have established that clearly. But we established something else too. The ice that killed us on the surface is the same ice that, from just a few meters down, begins blocking radiation dramatically. And from beneath the full 29-kilometer ice shell, the story inverts completely. The ocean under Europa's ice is one of the most radiation-protected environments in the entire solar system. The ice above provides more effective shielding than Earth's atmosphere and magnetic field combined. Whatever lives down there, if anything does, is not being bombarded. It is insulated from space by a shell of frozen water 2.5 times as thick as the deepest point in Earth's oceans is deep. In 2025, researchers at the University of Leicester published a theoretical analysis of scuba diving in Europa's subsurface ocean. Not science fiction. A thought experiment grounded in real physics, worked through carefully to see whether human divers could survive the environment. What they found shifted the picture. The ocean is potentially 60 to 150 kilometers deep. The Mariana Trench reaches roughly 11 kilometers. Europa's ocean may be more than 10 times deeper, but pressure is not straightforward there. Europa's gravity is only 13% of Earth's. Pressure increases with depth far more slowly than it does on Earth. At 100 kilometers down in Europa's ocean, the pressure is roughly what you would experience at 13 kilometers depth on Earth, deeper than any human has dived, but within the range of engineered submersibles that already operate routinely at 11 kilometers. A Europa submarine would not require radical redesigns. It would require extensions of existing capability. Temperature near the ice is probably around -2 to -4 degrees Celsius. Cold, but not frozen, because salt depresses the freezing point of water. Near the seafloor, if hydrothermal vents exist, the temperature could be very different. On Earth, hydrothermal vents produce water exceeding 300 degrees Celsius, kept liquid by the pressure above. Around those vents, entire ecosystems thrive. Tube worms, giant clams, shrimp, microbial mats. None of them rely on sunlight. They run on chemosynthesis, chemical energy reactions between hydrogen sulfide, methane, hydrogen gas, and available oxidants. Life does not need a sun. Life needs energy and chemistry. Europa has both. A 2025 study published in Frontiers in Astronomy and Space Sciences identified 3 types of Earth ecosystem that could serve as biological templates for what Europa might support. Deep sea hydrothermal vents, underground ecosystems powered by the slow radioactive decay of rock, and deep sea sediments where microbes survive on energy budgets so small they are almost incomprehensible. The lesson across all 3 is the same. Sunlight is not the requirement. Chemistry and energy are the requirements. And Europa offers both, drawn from 3 independent sources. First, tidal heating. Jupiter's gravity flexes Europa's interior constantly as it orbits. That flexing generates friction. Friction generates heat. That heat is the most likely driver of hydrothermal activity on Europa's ocean floor. Second, radioactive decay. Uranium and thorium in Europa's rocky core decay slowly, producing radiation that drives chemical reactions, radiolysis, inside the rock itself, releasing hydrogen and oxygen ions that can serve as chemical fuel. Third, the surface ice. Salt-rich ice near Europa's surface, bombarded by radiation, slowly becomes dense enough to sink. As it sinks, it carries oxidants from the irradiated surface down into the ocean over tens of thousands of years, delivering chemical energy from above. Europa's ocean may have been liquid for 4 billion years or more. On Earth, life appeared within the first billion years of liquid water's existence. Some evidence suggests it appeared within the first few 100 million years. 4 billion years is not close to the minimum. It is multiples of it. Europa Clipper will not answer the question of whether life exists there. It arrived at Jupiter in April 2030 after launching in October 2024, and it will characterize the ocean from above, measuring ice shell thickness, surface chemistry, ocean depth, and salinity via gravity and radar. If plumes exist, rising steam and ice from the ocean below, Clipper may fly through them, but it will not drill. It will not sample the ocean. It will tell us whether the conditions for life are real. The answer to whether life is actually there requires the next mission. A lander that touches down, drills through 29 kilometers of ice, and drops instruments into the water below. Or a plume fly-through mission that captures droplets already launched into space, samples already waiting to be collected. What we know about life's resilience suggests we should not assume emptiness by default. Deinococcus radiodurans is known among biologists as the world's toughest bacterium. In experiments on the International Space Station, pellets of this organism were exposed to raw vacuum for 3 years. 3 years of cosmic radiation, ultraviolet bombardment, and temperature extremes that would destroy almost any material. The outer layers of each pellet died, but in dying, they formed a crust, a shield made from the organism's own dead tissue. The inner layers survived. They were alive and viable after 3 years of conditions that would kill anything we know how to build. That is not a curiosity. That is a data point about what life can do when it finds a reason to persist. If Europa harbors biology, the implications reach far beyond one moon. Life would cease to be a singular accident on a fortunate planet. It would become what the chemistry suggests it should be, a natural consequence of energy and time. The universe would not be an exception built around us. It would be a system that, under the right conditions, repeatedly finds its way to the same destination. We have never confirmed biology beyond Earth, but we have never, until now, had the tools to look in the right places. And the right places may be closer than anyone expected. Titan waits at the edge of what human engineering can reach, offering fuel and flight and a surface that could, in time, become home. Europa waits beneath its frozen shell, patient and dark and possibly alive. Both of them are still just the beginning of what the outer solar system contains. And so the question shifts, not what nature has already built in the dark, but what we could choose to build ourselves. The year was 1975. NASA brought together scientists, engineers, and students at Stanford University for a 10-week study. The brief was direct. Design a permanent home for humans in space. Not a station, not a waypoint. A world. What they produced was the Stanford Torus, a rotating donut, 1.8 kilometers in diameter, 130 meters across the interior, spinning at roughly 1 revolution per minute. Centrifugal force on the inner surface would feel exactly like Earth gravity. Drop a ball and it falls. Pour water and it flows. Nothing inside feels different from standing in a field on a summer afternoon. But the picture is stranger than the description suggests. The ground curves upward on both sides. The landscape rises along the walls and arches overhead. If you look up, you see the other side of the ring above you, lit by mirrors mounted at the hub that redirect sunlight into the interior. The entire world is visible from where you stand. It would house 10,000 people, residential neighborhoods, parks, farms, fish ponds, livestock, closed-loop air, water, and waste recycling. A tiny self-contained Earth, spinning in the void. The Stanford Torus was never built. It was a study, an exercise in theoretical possibility. The physics worked. The engineering was hard but not impossible. The real bottleneck was always cost, always scale, always the absence of political will to begin. And it stayed that way, on paper, as an idea waiting. Then, in 1976, Princeton physicist Gerard K. O'Neill published a book called The High Frontier. O'Neill did not want a donut. He wanted cylinders. 2 enormous tubes, side by side, each one 8 kilometers in diameter and 32 kilometers long, counter-rotating in opposite directions, cancelling each other's gyroscopic effects. The interior of each cylinder divided into 6 strips running the full 32-kilometer length. 3 strips of land, 3 strips of window, alternating around the circumference. Sunlight enters through the windows. The land strips are lit as evenly as an overcast afternoon on Earth. Rotation provides gravity at the inner surface. The visual experience is unlike anything on any natural world we have visited. Flat ground beneath your feet, landscape stretching 32 kilometers ahead, then curving upward along the walls and arching overhead. Look up and you see more land. Farms, forests, lakes, hanging above you, bathed in sunlight from windows you cannot see directly. Clouds form naturally as the ecosystem matures. It rains. Wind patterns develop. Weather. Not designed weather. Weather that emerges from the system itself. O'Neill imagined people living full lives there. Not survival, not hardship. Communities with every variety Earth life allows. Skiing on engineered mountains. Sailing artificial lakes. Sports built around the geometry. A ball thrown in a rotating cylinder follows a curved path that no game on Earth has ever needed to account for. New games, new arts, new ways of moving through a world you can see all of in one slow turn of your head. In 2019, Jeff Bezos stood in front of an audience and made the case that O'Neill cylinders were not a fallback plan for a species that failed to colonize planets. They were the superior alternative. Every natural surface has unavoidable constraints. Mars has the wrong gravity and no magnetic field. Venus has an atmosphere that destroys everything it touches. Titan is extraordinary but cold enough to make metal brittle. A space habitat has none of those constraints. You engineer the gravity you want. You design the atmosphere from the start. You set the temperature and the light and the day length and the seasonal cycle. You control everything. Not fighting a hostile environment. Building exactly the right one. A single O'Neill cylinder 32 kilometers long and 8 kilometers across provides more than 300 square kilometers of habitable surface area. It could house millions. Build hundreds of them and you have a civilization of hundreds of millions, none of them on a planet, all of them in precisely the conditions human biology requires. The raw materials are there. A single metallic asteroid, 16 Psyche, currently being studied by NASA's Psyche spacecraft, contains an estimated $10,000 quadrillion worth of iron, nickel, and gold. That number is economically meaningless, but in material terms, it is enough metal to construct millions of habitats. The moon provides aluminum, silicon, iron, titanium, and oxygen. Asteroids contribute nickel, cobalt, platinum, and water. The materials are in the solar system already. They do not need to be launched from Earth. They need to be gathered and assembled, which is a harder problem, but a solvable one. The psychology of enclosed worlds is harder to model. Living inside a finite structure, however vast, differs from living on a planet with open horizons and an atmosphere that extends until it fades into space. Habitat designers have proposed a set of responses. Keep areas of the habitat out of line of sight from each other, so no single vantage point shows the entire world. Grow vegetation semi-randomly rather than in manicured rows. Allow weather to develop some unpredictability. Build in seasonal variation with day-night cycles. The goal is not to recreate Earth, it is to make the world feel natural, even though every detail was designed. And beyond the O'Neill cylinder, there is the Mercury cylinder. Theoretically constructed from carbon nanotubes, materials stronger than any metal currently manufactured at scale. A Mercury cylinder could have a radius of up to 460 kilometers. Its interior surface area would be comparable to the entire land area of India, one structure, hundreds of millions of people, of mountains, rivers, oceans, complete weather systems, entire ecosystems. The upper bound of what centrifugal engineering could eventually produce. A civilization built on space habitats would have one more advantage that no planet offers. Mobility. A habitat with an engine can adjust its orbit slowly, position near an asteroid for mining, move closer to the sun for energy, move outward for cooling. It is not rooted to any one location. It is, in a very real sense, a civilization that can move with the solar system's opportunities rather than being fixed to one point in it. The Stanford Torus was designed in 1975. The O'Neill cylinder was proposed in 1976. Nearly 50 years have passed. Neither has been built. The engineering challenges are immense. The cost is astronomical. The political will has not materialized. But the physics is real. The materials exist. The designs work on paper. This is not fiction. It is an engineering problem with an enormous price tag, and no one yet willing to pay it. But ask a different question. Not whether we want to build these things. Whether we might eventually have no choice. 66 million years ago, an asteroid roughly 12 kilometers across struck what is now Mexico's Yucatan Peninsula. The impact released energy equivalent to 10 billion Hiroshima-scale nuclear detonations. A shockwave, a heat pulse, a global firestorm, and a years-long winter of ash and debris. Approximately 75% of all species on Earth went extinct. The dinosaurs, which had been dominant for more than 165 million years, were gone. Not slowly, not in decline, gone in a geological instant. They had no telescopes, they had no space programs. We do. NASA's DART mission in 2022 deliberately slammed a spacecraft into a small asteroid moonlet called Dimorphos and successfully altered its orbit. We have demonstrated the ability to move an asteroid. That is not nothing. That is remarkable. But detection is incomplete. Approximately 34,000 near-Earth asteroids have been catalogued. New ones are identified regularly. Asteroids approaching from the direction of the Sun are the hardest to detect. Those are precisely the ones that would arrive with the least warning. And asteroids are only one item on the list. The Toba supervolcanic eruption, approximately 74,000 years ago, may have reduced the total human population to as few as 10,000 individuals. A genetic bottleneck so severe that the diversity of the entire human species today reflects that near-extinction event. Toba was not even the largest eruption in Earth's history. The Siberian traps, 252 million years ago, drove the Permian Triassic extinction, the single worst mass extinction in the history of complex life. 96% of marine species, 70% of terrestrial vertebrate species, gone, caused not by an asteroid from outside, but by volcanic activity on our own planet. Add gamma-ray bursts from distant stellar explosions, capable of sterilizing a hemisphere with virtually no warning. Add global pandemics. Add nuclear conflict, which has not diminished as a threat since the Cold War. Add our own industrial alteration of the atmosphere and oceans, which mirrors, in directional terms, the early stages of past mass extinction events in the geological record. In 2006, Stephen Hawking stated plainly that humanity must colonize other worlds to survive. The reasoning was mathematical, not romantic. Given enough time on a single planet subject to random catastrophic events, the probability of an extinction-level event approaches certainty. Not whether, when. All of humanity's history, all of its knowledge, all of its biology sits on one planet, one asteroid, one supervolcano, one catastrophic pandemic, one sufficiently destructive war, and the basket breaks. Then the pattern shifts. The argument for leaving is not only about survival. It is also about what is available if we do. Consider Venus. Earth and Venus contain roughly the same total amount of carbon. On Earth, most of that carbon is locked in rocks, in coal, in deep-sea sediments, in living organisms. Very little is in the atmosphere. On Venus, nearly all of it is in the atmosphere. The difference between a habitable world and a furnace is not how much carbon exists. It is where the carbon sits. We are moving carbon from rocks to atmosphere by burning fossil fuels. We will not turn Earth into Venus. The physics differ in important ways. The distance from the sun, the water cycle, stabilizing feedbacks. But the direction is the same direction Venus traveled. And even if we navigate every threat we can prevent, Earth has an expiration date we cannot change. The sun is slowly brightening. In roughly 1 billion years, increased solar output will begin evaporating Earth's oceans. In 3 to 4 billion years, the sun expands into a red giant and the inner solar system, including Earth, is consumed. These timescales dwarf human civilization by a factor that is genuinely hard to hold in mind, but they are real. They mean that even in the absolute best case, persistence eventually requires leaving. The resources beyond Earth are not a luxury. A single metallic asteroid contains more iron and nickel than humanity has extracted in all of human history combined. Water ice in Saturn's rings could supply billions. The sun's total energy output exceeds humanity's current energy use by a factor of billions. We are a species living on 1 grain of sand on an infinite beach, deliberating whether to explore the rest. And every hostile world we have visited is a classroom. Venus teaches us about runaway greenhouse chemistry and atmospheric collapse. Mars teaches us about habitability erosion and what happens when a planet loses its magnetic field. Europa teaches us that life may not need sunlight. Titan teaches us that chemistry can organize itself in ways we never expected. Each death scenario is a lesson. Each lethal surface contains data we cannot get anywhere else. In 1950, the physicist Enrico Fermi raised a question over lunch that has never been fully answered. If intelligent life is common in a galaxy of hundreds of billions of stars, billions of years old, where is everybody? The galaxy should be teeming with signals, with evidence, with the unmistakable marks of other civilizations. We see nothing. One possible answer is this: civilizations tend to destroy themselves before becoming multiplanetary. They deplete their resources, poison their atmospheres, wage species-ending wars, or fail to develop the technology to leave before a cosmic event erases them. If that is true, then becoming multiplanetary is a filter test. The civilizations that pass it persist. The ones that do not, vanish. We do not know if we will pass that test. We do not know if any species ever has. Staying on one planet is not a strategy for long-term survival. It is a strategy for hoping that nothing goes wrong. Now, the final accounting. Not which world kills us fastest, but which worlds we might actually live on. Every world we visited left us with a number. Neptune, less than 2 minutes before the winds destroy the suit. Jupiter, roughly 3 minutes before radiation, pressure, cold, and wind shear overwhelm everything simultaneously. Uranus, 3 to 5 minutes as the frigid, dense atmosphere conducts heat away faster than any thermal system can replace it. Saturn, approximately 5 minutes. Pluto, about 8 minutes before the cold makes soot, materials brittle and seals fail. Mercury, around 15 minutes once the sun is fully up. Europa, 15 minutes before radiation begins taking systems apart at the cellular level. Venus, 20 minutes before the temperature and pressure and acid defeat every defense we currently know how to build. Titan, 2.5 hours. The most livable alien surface in the outer solar system, still ultimately cold enough to kill. Mars, 10 hours on the life support of one EVA suit, the longest window any world offers us. Survival time and colonizability are not the same measurement. Tier 1 is Mars, not because it is the best option, but because it is the closest realistic one. SpaceX's Starship, NASA partnerships, robotic precursors, 3D printed habitats, bioplastic greenhouse domes with living algae walls, ISRU, fuel production from Martian air and ice. The engineering path exists. The timeline has slipped. The challenges are enormous, but Mars is the world we are building toward first. Tier 2 has 3 candidates, each with elegant physics and a harder problem. Titan has more natural resources than any other body in the outer solar system. Its atmospheric pressure is manageable. Its radiation environment is safe. Human-powered flight is physically possible there in a way it never will be on Earth. The obstacle is distance. 6 to 7 years of travel each way. A communication delay that makes real-time support impossible. A supply chain that must be planned half a decade in advance. The Venus cloud layer at 50 kilometers altitude offers temperature, pressure, and gravity nearly identical to Earth's surface, all within the same environment. The physics of a floating habitat there is elegant. Breathable air is its own lifting gas in that atmosphere. The engineering challenges are significant. The acid resistance problem is unsolved. But Venus is closer to Earth than Mars is, and the physics is on our side in a way that is genuinely unusual. Orbital habitats near Earth, Stanford Torus and O'Neill cylinder designs, offer the purest version of the colonization argument. Total control over every parameter, no hostile environment to fight, exactly the conditions you choose. The challenge is scale. Asteroid mining infrastructure does not yet exist, but the advantage is building precisely what you want from scratch, rather than adapting to a world that is trying, in its way, to stop you. Tier 3 is the long future. Europa's subsurface colonies, beneath 29 kilometers of ice that shields the ocean below from radiation more effectively than Earth's own atmosphere and magnetic field combined. Mercury lava tube settlements, permanently shadowed and thermally stable, isolated from the radiation and heat that make the surface lethal. And the largest O'Neill cylinders, McKendree-scale structures, nations enclosed in carbon and light, each one housing hundreds of millions of people in conditions tuned exactly to what human biology needs. These are not impossibilities. They are engineering problems on very long timelines. Astronomer Jill Tarter spent decades leading the search for signals from other civilizations. Her conclusion was not hopeful in the conventional sense. Humanity is a small, fragile species on a small, fragile planet in a vast universe that does not care whether we survive. That is not depressing. It is clarifying. Our survival is our responsibility. Nobody is coming to save us. The tools to answer whether we are alone are already being built. The James Webb Space Telescope is studying exoplanet atmospheres for biosignatures, the chemical signatures of life altering a world's chemistry. The Europa Clipper is now on its way to Jupiter's ocean moon. NASA's Dragonfly will one day land on Titan's surface and search for the chemistry that precedes biology. A proposed habitable worlds observatory would directly image approximately 25 potentially Earth-like planets around nearby stars. We may have an answer within decades, and the answer, either way, transforms everything. If we find life on Europa, or in Titan's methane lakes, or in the clouds of Venus, or in the atmosphere of a world orbiting a star 40 light-years away, then the process that produced us is not unique. Chemistry, given the right conditions and enough time, finds its way to biology. The universe is not a place where life is a singular accident. It is a place that, repeatedly, under the right circumstances, learns how to look at itself. If we find nothing, that is equally transformative. We may be the only consciousness in a galaxy of 400 billion stars, the only species that has ever looked up and wondered. Our survival becomes not merely important but something closer to sacred. Our extinction would not be a local tragedy. It would be the universe losing its only known way of knowing itself. Every world we visited this evening tried to end us. Every world also taught us something we could not have learned anywhere else. Venus showed us what happens when carbon migrates from rock to sky. Mercury showed us the price of proximity to a star. Mars showed us how a world loses its protection and its water and its future, slowly, over billions of years, without anyone to witness it. Jupiter showed us scale so far beyond human experience that engineering must be reconceived from the beginning. Europa showed us that life may not need sunlight at all, that an ocean sealed under ice for 4 billion years may be the most stable habitat in the solar system. Titan showed us that chemistry organizes itself in ways we never anticipated, in liquids we never expected, under conditions we barely understand. Neptune showed us that the universe has no interest in slowing down for human comfort. Pluto showed us that even at the farthest edge of everything, there is beauty worth finding. The solar system is our nursery. Every lethal surface is a classroom. Every hostile world is a lesson dressed as a threat. Picture a human being, wings outstretched, gliding through Titan's orange sky. Saturn's rings hang overhead, impossibly wide, catching light that has traveled 1.4 billion kilometers from a sun that looks like a bright star rather than a disk. Below, a methane sea stretches to a horizon that is lower than any horizon on Earth. Closer, the world curving away faster because Titan is smaller. The air is dense enough to feel. The wings catch it. Flight works. Picture a submarine descending through Europa's ocean. Searchlights cutting through water that has never seen the sun. Water that has been liquid for 4 billion years, sealed beneath ice, stirred by tidal forces from a planet so massive it raises tides in solid rock. The beam sweeps the dark. Something moves through it. Something that should not be there. Picture a city floating in Venus's upper clouds. Sunlight coming through translucent walls. Below, acid clouds the color of gold drift in patterns that have circled the planet for decades, for centuries. The colony holds its altitude without effort because the air inside it, the air its people breathe, is lighter than the air outside. The physics keeps them up. Picture an O'Neill cylinder turning slowly against the black. Rivers inside it. Forests. Mountains that curve upward and become, from one angle, a sky. A child looking up and seeing land overhead, lit by sunlight entering through windows at the cylinder's edge, understanding instinctively that the world is round in a direction no child born on a planet has ever had to grasp. These are not fantasies. They are engineering problems. Hard ones. Some of them decades away. Some of them centuries. But the physics is real. The chemistry is there. The materials exist in the solar system already, in asteroids and moons and rings, waiting to be gathered and shaped. The species that learned to split atoms and walked on the moon and built a telescope, now seeing the birth of galaxies 13 billion light years away, is not going to stop here. That is not arrogance. It is a pattern. We have never, in all of human history, looked at a horizon and decided the horizon was enough. The solar system is large. It is old. It is, in almost every direction, immediately lethal to anything wearing a human body, and it is ours to learn, to reach, to one day fill with versions of home that do not yet exist, built from materials we have not yet gathered, by people who have not yet been born, on worlds we have not yet touched. The work has already begun.